All right, hey, what's up, everyone? Thank you for your patience on getting this lecture and this video back. It's been a week for sure, but we'll go ahead and try and get this started and get it knocked out. So if you remember back, what was that? Probably last Wednesday, a week ago, we were talking about the different types of clay minerals. We had our 1-to-1s, and then we have our 2-to-1s, where we have water that can get in between like the vermiculite and the montmorillonite and cause that shrinking and swelling. We have our 2-to-1 chlorites, where we have this octahedral and tetrahedral, basically the sandwich, two sandwiches bound together by that octahedral layer, and that doesn't have any swelling. And then remember that we have our micas that have that potassium, that when that water, when the water gets in between those two clay layers, those 2-to-1 clay layers, and it expands, that potassium can get trapped inside of this kind of hole that structure makes. So it gets kind of locked in there, and it is not likely to come back out once that, even if that clay layer opens and closes. We talked about these aluminum and iron oxyhydroxides. It's mostly just that there's only aluminum inside those, inside the tetrahedron. For example, this is gibbsite. And then we talked about organic matter. And so this is kind of where we're leading into talking about charges. And so the net charge is negative on this entire structure. But there are some positive charges on there as well. So, but the overall net charge is negative. And we have some hydrophilic and some hydrophobic sites. And so that is going to influence how the water holding capacity of this organic matter. So if you recall, I think we left off pretty much right here where we were talking about isomorphic substitution, and that this is a source of permanent charge. Like, this is not likely to change. When those clay layers were formed, or when the clay layers were formed, like I said, 400 million years ago, the minerals that are in that structure are there. It's not that they can be replaced. So isomorphic substitution, iso meaning similar, and morph meaning size and shape. It is not the charge. If it were a 1-to-1 charge exchange, then there wouldn't be any charge exchange. So the deal with isomorphic substitution is that when that clay layer was made, when that colloid was made, either aluminum or silica is in the tetrahedral, and either aluminum or magnesium is in the octahedral. It's either one of those two, either or. It just so happens to be how much of the concentration of that aluminum or silica was at the time when it was being made. So remember that we have substitution in the tetrahedral is going to be silica for aluminum, or aluminum for silica, whichever. And octahedral is going to be aluminum replaced by magnesium. And so remember, we looked at the charges, that oxygen always being -2. We see that we have a -8 here in the the tetrahedron. A silica +4 makes that charge a -4. So the charge on this tetrahedron is -4. When we moved over here to the octahedron, our oxygens are worth -2. We have 6 of those with 1 aluminum 3+. Therefore, the net charge on that is 9. So remember, we went through this and we showed what it looks like for a 1-to-1 tetrahedral and octahedral. If you remember, we went back over what the charge is, the difference between all these oxygens and then the positive cations, and how that balanced out. On the right side, we exchanged aluminum for silica and magnesium for aluminum. We did some math, and we found that when we have that substitution, there is a change in charge of -10 charge sites. Again, remember, this happened when it formed. We cannot go out there and apply extra magnesium and expect this to change. That's why it's called permanent charge. Now, what can change, and it's in the name, is this pH dependent charge. And it's dependent upon the pH, right? I know, it's in the name. And so what we have is remember that big, large piece of organic matter, and we've got a much kind of more condensed version of that. But there are three sources of pH dependent charge: functional groups of organic matter, aluminum and iron oxides, and broken edges of clays. Now, the broken edges of clays account for very little of what we would think of with pH dependent charge, and that because it's really hard to break something that's that microscopic, right? But it does happen. Those aluminum and iron oxides, we're going to see most of those in our highly weathered oxasols, or those gibbsite materials, such as we saw a few slides previous. But for the most part, it's going to be that functional group of organic matter. And so we have these functional groups of organic matter out here on these phenolic rings. Now, I'm not necessarily concerned that you know that this is a carboxylic group or that this is an alcoholic hydroxyl group. This is not organic chemistry. But some of the principles that apply in chemistry are going to be applied here when we're talking about this pH dependent charge. So, three sources of pH dependent charge are going to be functional groups of organic matter, aluminum and iron oxides, and broken edges of clays. So let's look at how this happens. And so we haven't made it into pH, that's our next module, but we know from general chemistry that when a solution or soil is acidic, the hydrogen concentration is great. pH is a measure of the hydrogen concentration. And so that if we add lime to a soil because the pH is decreased, that it becomes more alkaline and we increase this hydroxyl concentration. So as pH increases, hydrogen content decreases. As pH increases, hydrogen content decreases, which means that the hydroxyl concentration increases. So what we have here is we've just applied lime to our soil and we've increased the hydroxyl concentration in the soil. Because soil is because they're trying to reach an equilibrium, this hydroxyl with this negative charge needs to find a partner. And so what happens is the hydroxyls that are on the hydrogen as part of the hydroxyl in those functional groups of organic matter will dissociate from the functional group and bind with the hydroxyls in the soil solution to form water. Now, it's not like a cup of water or something that we can take out of the soil, but that it forms like a water molecule. When I think about like the size of what this water molecule is, we're talking Avogadro's number. That's 6.02 times 10 to the 23rd. It's forming like one of those molecules, okay? But what happens is that now there's a negative charge left on those functional groups of organic matter because the hydrogen has dissociated. So now we increase the cation exchange capacity. So anytime we increase the negativity or the negative sites within the soil, we increase the cation exchange capacity. So as pH increases, CEC increases. All right? So we have this exchange, we have this dissociation. Those hydrogens have dissociated from that functional group of organic matter, has formed these little water molecules. So what happens over time as we apply fertilizer and as our plants are doing the thing they're supposed to be doing, which is growing, They have plant metabolic processes that are releasing hydrogen into the soil so that they can take cations up, and eventually our soils become more acidic. So acidic soils have a greater hydrogen concentration. So, go back. So as we increase the hydrogen concentration, we see that those hydrogens have now associated or protonated those functional groups of organic matter, bringing it kind of back to where it was before that pH change. If we get too much hydrogen, what we can have is we can have a protonation of that functional group of organic matter and get a positive charge. Now, this is going to change back and forth. That hydrogen is going to move because the charges in this phenolic ring are constantly changing. We have to have a large hydrogen concentration within the soil, so our pHs are going to be like 3.5, 4.0. Again, highly weathered aluminum and iron oxyhydroxides. When I think about this, I think about Brazil. They have problems with phosphorus and nitrogen applications because their soils have this pH and this organic matter, and that pH dependent charge is now actually working the other way, so that there's a greater positive charge, or AEC, our anion exchange capacity. So remember that as pH increases, what happens to the CEC? pH increases, CEC goes up. So if the CEC goes up, that means that the AEC must go down. Well, in acidic soils, if the pH goes down, then the AEC goes up. And if the AEC goes up, then that means that the CEC goes down. So there's this inverse relationship between pH and CEC. Did I say that right? An inverse relationship? pH goes up, CEC goes up. pH goes down, CEC goes down. Not an inverse relationship. Anyhow. So what we have is we have this positive charge, and this is going to change back and forth, so that as our pH changes in the soil, it really influences the nutrient availability, because now some of our nitrates and our phosphates are now held to this functional group of organic matter, and it's not likely to be released. So when we're talking about the absorption of these cations and anions, we have different like diffuse ions like calcium and magnesium, and these are going to form more outer sphere complexes. And when we think about outer sphere complexes, the difference between outer sphere and inner sphere is that there is a water molecule that is kind of surrounding how that cation is held, kind of like a bubble, so to speak, of how that's adsorbed to the soil colloid. And remember that we talked about the lyotropic series, and that the greater the charge and the smaller the hydrated radius, the stronger the attraction to the soil colloid. I'll say that again. The greater the charge, so let's say aluminum 3+, for instance, high charge, high charge, small hydrated radius, which means it doesn't hold a lot of water around it. It's going to be held very strongly to the soil colloids. These outer sphere complexes don't have that. So we have calcium 2, which has a larger affinity for water. It has a larger hydrated radius, a less charge than aluminum 3+, but it has more water around it. And so the attraction between the calcium and the cation exchange site, there's kind of a buffer zone there. Next, we have inner sphere complexes. And with inner sphere complexes, there's no water molecule, and these are more strongly adsorbed to the soil. So this happened to be more for our anion absorption, where we had phosphates and sulfates, and nitrates, those anions, are actually going to be held tighter to the soil, to the colloids, because they don't have an affinity for water. So to look at this, here we have calcium 2+, and we have these little water molecules surrounding it, and then that charge is actually one of these hydrogens from the water molecule and the oxygen from this tetrahedral. Actually, this looks like it's in the octahedral. So this is for gibbsite, or looks like kaolinite. And so the hydrogen is weakly attracted to that. And so this calcium doesn't really have a charge going too much to that, right? Because there's this water boundary around it. Now for phosphate, over here, we have this hydrogen. Notice that this has now switched, and if we move up here, we see that the phosphorus is now bound with these two oxygens, and this is now left out there. So there's no, this is like a direct bond. This is actually a covalent bond. So the biggest difference between outer sphere complexes and inner sphere complexes. So outer sphere complexes are going to be like a magnet, and that they will connect, and there is a little layer of water which allows them to easily exchange. But for inner sphere complexes, they're covalently bonded, so they share electrons in that outer shell. I know it's going all the way back to chemistry, but just understand that it's a stronger bond for an inner sphere complex than it is for an outer sphere complex. So when we talk about cation exchange reactions, these are just some basic kind of laws of cation exchange, that it's a 1-for-1 exchange, so that it takes one hydrogen to exchange with one sodium. But it would take two hydrogens to change with a 2+. And it would take three hydrogens to dissociate an aluminum 3+. And so these can go back and forth, and this is going to change. It just depends. Again, this is going back to that diffuse double layer where we have all of those anions and cations vying to be kind of held stable by that soil colloid. So reversibility just means that it can be a 1-for-1 exchange, which kind of goes back into what charge equivalence is that if you have a calcium 2+, then you would need at least two hydrogens to dissociate that, or a magnesium 2+. Or if there were three calciums, it would take two aluminums. It's just a charge equivalence. This is not like isomorphic substitution. This is about the charge. This is about the electronegativity and the magnetism of the soil colloid and the cation. So here what we have is, in order, so here we have our plant, we have our root hair that is exchanging hydrogen out. It is creating this electrochemical diffusion gradient, so that we have two hydrogens that now replace this calcium 2+, and that calcium 2+ can now move into the plant. And so this is how plants get the nutrients off the soil colloid and into their tissue, so that they can perform the functions that they need to perform, primarily photosynthesis. So we would only need one hydrogen to displace one potassium that can be taken up. So that charge equivalence has to happen in order for this hydrogen. And remember that hydrogen is held greatest to the soil colloid, equal with aluminum 3+, and then calcium 2+ being the third strongest, right? So this is all about charge and hydrated radius. Larger hydrated radius, easily exchanged off the soil colloid and taken into the plant. There's a ratio law that starts when we start getting into a little more complex, where we have multiple colloids, multiple cations in the same soil solution. And all this is saying is that if there are going to be, if there are 20 calciums and we have magnesium, then the charge needs to be equal. Like there's only 20 charges on this mycel. But we can have some exchange and have 4 magnesiums and 16 calciums. And so it's kind of standard that the ratio for calcium to magnesium is 4:1. Because remember, in that Lyotropic series, they're fairly similar. But calcium is a little stronger, so it's going to take over a few more of those charges. It has between calcium and magnesium, it has actually a smaller hydrated radius. So magnesium has a larger hydrated radius than calcium. That's why it's not held as tightly. So here we are back to our Lyotropic series. We have aluminum, calcium, magnesium, and potassium, which is equal to ammonium, and all are greater than sodium. So that's affected by the charge and the hydrated radius. So that the greater or the higher the charge and smaller hydrated radius are held more tightly, which means the opposite. Lower charge, sodium, with a large hydrated radius, is not held as tightly. And then finally we have complementary cations. And what this is saying is that there's kind of this array of cations that are typically exchanged in pairs, or kind of like as a group. Not that we'll be mentioning any of this, or like that you'll need to know what the ratios or how they are exchanged off of, but you can see we have this group over here, and we see that the aluminum, no exchange, right? Because it's held the tightest. We see that sodium exchanged a lot. We actually exchanged sodium for ammonium. We have a couple of magnesium that dissociated, and it looks like a few potassiums exchanged off of there as well. All right, so maybe that helps you understand a little bit more about cation exchange capacity, and a little bit about anion exchange capacity as well. So when we talk about CEC, it is the sum total exchangeable cations that a soil can adsorb. And we measure this in centimoles of charge per kilogram. This is more of the scientific term. If you read it on a soil report, it will just tell you, you'll likely see it as centimoles of charge per kilogram. It's just a unit of measure. So if you have a CEC of 15, you see we have a CEC of 25 or a CEC of 5. Like this is the max amount. This is CEC is the it's the cup. It's the size of the cup, right? And so on the right we have a small cup. On the left we have a big cup, and the difference is that the texture. We have more clays, and more clays have larger surface area and more of those negative cation exchange sites. So we can hold more nutrients in a clay than we can in a sand. So that's where texture by feel comes into play, is that when I know that I pick up a handful of soil and I get some sandy return on that. Like when I go to do texture, and remember the ball dropped and it just kind of, there's nothing holding that soil together, which means there's no exchange sites. There are very few exchange sites, but when we have a clay soil and we can make that long ribbon, like I can pick up that handful of soil and automatically know generally whether it has a small cup or a large cup based on texture. When we go to measure the CEC, so when you send off a soil test, which we'll be doing here in a couple of weeks, we'll actually go out and we'll take the soil samples and we'll get the results back and we'll interpret those. And so what they'll do is they'll measure the soil as is. And what they do is they take some air dried soil, they add some water to it, and then they just kind of measure that. But they use the buffer CEC, they increase the pH, they manipulate the pH dependent charge of that soil, and they figure out how much, like what is the actual potential should you raise that pH. So you'll get like an effective CEC, which is just as is, and then you'll see this buffer CEC, which means that we have manipulated it to find out what the actual maximum potential cation exchange capacity is for your soil. And here we are again with our pH dependent charge, that the more acidic the soil, the less CEC, and that the more alkaline the soil, the greater the CEC. So as pH goes up, what happens to the CEC? The CEC goes up. As pH goes down, what happens to, listen, as pH goes down, what happens to the AEC? When pH goes down, the anion exchange capacity increases because the CEC decreases. All right, and so kind of the ways that we can measure these exchangeable cations in the field, they have percent base saturation, which you would get on a soil test report. They'll look at some of these complementary and antagonistic cations. Calcium potassium is limited because calcium 2+ actually holds on to most of those soil colloids in the CEC, but also that it will exchange off and be taken up into the plant because of that higher charge. So for our anion exchange capacity, we're mostly going to be concerned with our intersphere complexes. Remember, intersphere complexes do not have the water surrounding them, and they form those covalent bonds, right? And so this comes into our anion exchange capacity and that strength of ion absorption. So here we see we had phosphate, HPO4 2 negative, SO4 2 negative, and then we start getting into our weaker anions like nitrate and chlorine. And so because of the charge, and also that nitrate and chlorine are also very water soluble, they're weakly adsorbed compared to phosphates and sulfates. And so this is going to happen, again, I mentioned in highly weathered acidic soils. So we're looking at oxisols and altisols, where we can start to have some of that highly weathered material. We have aluminum and iron oxides. Low pH is actually going to increase the anion exchange capacity. Remember, as pH decreases, anion exchange capacity increases. And so this actually goes into, this is important for when we're talking about like pesticide and groundwater contamination. We have these problems with some adsorption or some complexation and partitioning, and the way that those organic compounds are held by the soil CEC. So this is actually, what they did is they added Bacillus thuringiensis, which is this bacteria that is used in BT corn. But they applied this to the soil and they found that more of the toxin was absorbed by the montmorillonite or the smectite. So this is a 2-to-1 clay, high shrink swell, high CEC, and this is our kaolinite. So like one tetrahedral, one octahedral, just stacked on top of each other, no shrink swell. So remember that charge happens on the tetrahedral, and what they found was that after a certain period of time, the kaolinite was only able to absorb about 150 of the 500 micrograms that was added to the soil. The montmorillonite, however, was able to absorb almost 400 micrograms of the Bacillus thuringiensis. So, kind of in agronomy, one of the things that we are tasked to do is to try and figure out and understand why things did or did not work. We're presented with these problems and we go, how come? Why didn't that work? And I did everything I was supposed to, and Farmer John goes, now, Dr. Nattrass, I don't understand. I did everything like the label said, and how come this herbicide didn't work there? Well, in this particular instance, in the A horizon, they had alpha sols with a low CEC. So we had like this kaolinitic surface horizon, sandy, low CEC, but we have this argillic or clayey CEC in the subsoil. And so what happened is that when the bulldozers kind of leveled that ground, so the bulldozer had previously leveled the ground in order to plant this field. And when they did, they moved some of that subsoil up, brought up by the termites, and there was a larger CEC in these areas, and that CEC actually held on to those herbicide molecules, and it was not available to the plant to be taken up. So there may be a thing on a herbicide label that says if you have a sandy soil, you only need to use this much. If you have a clayey soil, then you only need to use that much. All right? And then just to look at some of the partitioning coefficients, kind of how they determine which of these herbicides are going to be held more tightly to the soil. All right, that's all I've got for this one. I think in the next video, we'll go over base saturation and how to calculate CEC. All right? Thank you so much for your patience.